Hi all. Less than 2 weeks ago, we had a first look at the Pydantify project, a CLI tool that can generate Pydantic classes from the Yang files that your vendor provides to you. We discussed how this can be the way to do this low-level network automation in a more, programmatic way with less Jinja, less runtime errors, and more validation and native language constructs. Now, for the simplicity's sake, the example that I used was quite basic, something that you would probably start with, but you will not run with it long term. Probably your network automation stack will be more complex, more verbose, and more feature rich at the same time. So I wanted to take this up a notch and see how can you then use Pydantify when you try and build something that is more usable beyond the basic demo. So today we'll look at three examples how you can take this basic example of just raw classes that Pydantify generated for us and create some abstraction on top of it so that you can reuse objects more, so that you can have some inheritance in place and maybe some decomposition and structuring with your code. So kind of taking this more into the realistic domain rather than just a demo. So what we will look at is a basic demo topology with two SR Linux nodes. They are connected back to back together again, super simple topology, nothing crazy here. And we will take this step by step. First, we will configure just the interface on the two devices. Then we will see how we can mix in some abstractions on top of it. And lastly, we'll look at the tests and we will look at the concurrent execution with Nornir. So this is going to be interesting. Let's go. All right, so first I want to deploy this lab with two SR Linux nodes. So this is really easy with some clever stuff that we provide to our users. Just container lab deploy and the URL that creates two SR Linux nodes with one interface interconnecting them. So I will create this lab, and while it's spinning, we will have a look at the basic example that we had. So this was the basic example that we end up with two weeks ago. We created an Ethernet 1.1 interface. And as you can see, this is kind of verbose and hairy. You can't even argue how is this even better than a Jinja template. It's still a lot of stuff mixed in together. There is no decomposition. There is no reusability in that particular function. So even though it works, it is something that looks ugly and really not the way to approach your network automation when you have a real task at hand. So how do you take it step by step? Instead of just diving to, full-blown inheritance and factories and all the good stuff that you can build with Python, how can you kind of iterate on this? So I think the first example that can be taken from this ground zero is an example which I host under the v2 directory in the Pydantic SR Linux repository. And of course, this is all will be part of the GitHub repo that I will share in the description so you can replicate the use cases and execute the same commands. So what we're looking at is v2 of the same interface configuration tasks. But now here, look at this. Instead of creating this big interface list entry that we did before, we kind of structure it. And we have a structure here done in a way that instead of creating a subinterface list entry in place, we create a function that will create this subinterface list for us. So let's do the comparison. So this is the v2 interface on the right-hand side, and on the left-hand side, the same stuff done all at once. So you can see how this can simplify your interface creation in this particular case, but it can be anything. It can be, network instance or BGP neighbor. If you just use a simple function that takes in parameters and create at the same time the same thing here. So what we actually create in this sub-if function is we create this list. And this list will have the subinterface list entry with the embedded VLAN container and with the single tagged container using the ID that we provide as an input here. Well, it makes your code less hairy, less complex, easier to read, and there is some decomposition in place. So you can change your sub if function that I have here and maybe add more parameters to it or change the way you want to add VLANs. And at the same time, it still works exactly the same way. So if you execute this function, you will create an interface on SRL1 host. This is the first iteration that I did when I was going through simplification of the initial function that we had. But again, this is something that still lacks some reusability. And when we create this subinterface, what if we want to create, two of them? We can, of course, nest another function with another index and another, and kind of create those subinterfaces. But then it would be probably better if we would go a little bit smarter about these tasks. So if you go to the v3 directory in the repository, you will see a different approach to the same problem. So now you have some classes that you will work with. So instead of using the basic Pydantic classes that Pydantify created for us, you can create your own classes and kind of hide the ugly names that sometimes come out of the Yang stuff and create some meaningful names. Like when I create an interface, I can just instantiate an object from the interface class that I create, and I can provide a name for it so that the interface is being created. Before we look in this interface object, have a look at the style that has changed compared to the previous example. Now we create an interface, then we separately create a subinterface, then we can set a VLAN for the subinterface. So this is the method on the subinterface class, right? And then we can add subinterface to your interface. Now you see how this is more in the decomposition kind of paradigm. You create different objects and then you assign one to another. So if our interface consists of subinterfaces and a subinterface can have a VLAN, then we can create those three objects separately and then make up the relationship between them by just using the convenience methods that we create ourselves. Now, let's see how it's done, because this is probably the biggest change from the previous examples. Now we mix in some classes and we create some functions. Let's open up the interface class, for example. So the interface class subclasses the interface list entry. This is the class that has been provided for us by Pydantify, and we're also subclassing from this config object. And then we kind of init the original interface list entry class so that we have access to all the fields that Pydantic provides to us. We also create a property so that we can get the path of the interface that we are creating. So this path can be either hard-coded, and this is exactly what we did in v2, for example. You see in the set command function, we provided the path manually. Because we operated with a single interface, it was easy for us just to hard-code it and say interface name Ethernet11, and off we go. But now when we do more like decomposition and structuring of our code, it makes sense that our class could have provided to us the path that is associated with it. So when we instantiate an interface object, we can just say, hey, my path for the interface object is /interface name equals the name of the interface. So now we do not need to hard code it, and it's going to be very conveniently provided to us as a property. And then, as I said, the cool part is that now you can make up the relationship between the objects. With an add sub if function, I can just take in a subinterface class or object and add it to my subinterface list. So all of that stuff is not something that I wrote. It comes from Pydantify. It comes from the model that Pydantify generated for us and expressed as Pydantic models. So we just access the same fields, but we hide it under our own custom classes so that we can create some convenience functions like add subinterface. Okay, so this is the general idea. You decompose the objects that you want to work with, like interface, subinterface, VLAN, and then you can create them separately and make up the connections between them. Another example is when we create a subinterface, which is, again, just a basic subinterface list entry, and we create a set VLAN method for this class. Now, what set VLAN does is that it takes a VLAN object and assigns it to the VLAN field of subinterface object. And that is how we can create a VLAN separately, create different VLANs, and then assign them to the subinterface based on our design. So that is the general idea here. That is the way for us to decompose the complex operation of creating different lists, containers, and then make up a configuration object that is created based on the relationship model that we have designed for our particular automation function. So I think maybe it makes sense to execute this one so that we can see what's going on. All right, so I'm back at my terminal, and we will connect to the SRL1 node right away. So now I want to execute the v3 example, which uses some classes and still just creates an interface. So I want to install a watch with 1 second interval. And now when the watch is installed, we see that we only have a basic configuration of the Ethernet 1.1 interface. There's nothing inside this interface that makes it enabled with IP addresses and VLANs and encapsulations. So we will have to execute our example. So we will say Python example v3 and the interface script. So let's run this. So as you can see, we got our interface configured with the subinterface 100 and the associated VLAN. But what's interesting is that down below, you will have a log that will basically say, this is what happened. So I have this debug message that says for the Ethernet 1.1, the path was Ethernet 1.1, exactly as we expected. The name of the class object got passed to the path property, and we get this property nicely displayed for us. And that was the payload that we sent. As you remember, there was no kind of JSON serialization. That was all done behind the scenes. We had no manual parsing of any of that stuff. There were no templates involved. We worked with classes, and the serialization has been provided by Pydantic automatically. And then we sent this HTTP post request using the AstroLinux's JSON RPC interface, and then we got the response back, which I also log here. It was all good. There were no errors, and that makes up the demo. Just configuration is not everything that you have to worry when you kind of start creating more serious network automation. You also need to have tests. So let's look at one. Now for testing, the interesting part is that there are a lot of stuff that you can test here. You can test individual components, like you can test if your VLAN class that you use here produces the payload that is expected. You can test the end-to-end configuration. You can spin up the container topology in a cloud, like in a CI/CD instance, and then test that the interface has been created. Maybe you want to output some show commands and see that it all kind of maps together nicely. But what I wanted to show here as far as testing goes is that it is quite easy also to use these native Python constructs that we are working with here and make use of them in the testing. So I used pytest here, and I was just making up some trivial and maybe not so useful test, but just to make a point how you can use that in testing. You're looking at these two functions that are testing the VLAN class that we used for VLAN association. So I have this parameterized function for VLAN, and I provide like 3 different IDs. And what I test here is that when I use my VLAN class that I created, and then I output it to JSON, and then when I deserialize it, I can access the deserialized fields and compare that the VLAN ID, for example, can be accessed by this path, and it will be equal by the VLAN ID that I set. So this is kind of testing the correctness of your VLAN class, that it provides the correct payload, because at the end, what happens is that you are sending a payload to the device. So you need to make sure that your payload is expected to be correct based on your tests and your design decisions. So here we are asserting that the JSON blob that we will generate for the VLAN object will be correct, and we will be able to see the VLAN ID that we provided as an input to the VLAN class creation. The second function is testing the negative cases. Like we want to make sure that our validation works. And one of the interesting parts about schema is that sometimes schemas have validation embedded, like comparing your inputs to some regular expressions or having boundaries like the greater than or equal to specific values. So here I know that my Yang model for SOLinux does have checks for, let's say, VLAN ID ranges. It cannot be a negative number and it cannot be more than 4K94. So I can create a test that verifies that validation still happens before we kind of send the payload to the device. It happens on the client side. So if I run these tests, so I can use VS Code integration, you can see that it all passes for the 3 VLAN IDs that we provide. That means that all of these 3 values have been gone through the VLAN class instantiation. We serialized a JSON payload, then we loaded it up, and we made sure that we can access the VLAN ID by the provided path. We can also test the negative cases as well. So if I execute this one, again, it all passes, 2 passed cases. And we also verify that the message that the validation emits to us matches what we expect. As I said, this is not something too complicated, too crazy, and maybe even not so useful, but just to make a point, because writing tests is a task on its own. So I did not want to spend a lot of time just creating tests, but you can see how you can test things much more concisely because you work with native Python classes, Python objects, and you can create tests for whatever you want. You want to test a payload against a golden JSON blob that you might have crafted, feel free to. If you want to test the access by paths, this is the way to do it, or one of the ways. Okay, now let's talk about something even more complex and feature-rich. So far we worked with a basic example where we configured just one interface and that was it. What if we want to make some concurrent application of configuration to our devices? Because that is what you will all have eventually. You do not just go device by device and apply the changes. You have many devices, and a change usually targets a set of devices that you have. So what can be done about this? Now in Python, there are many ways how you can concurrently apply things to the network elements. You can either use raw threads, you can use multiprocessing, you can use async paradigm, but you can also use Nornir, and Nornir is one of the frameworks that makes it really not that hard to work with concurrent execution. For Nornir use case, we will create a topology. We'll still use the same topology with 2 SOLinux nodes, but we will create an ISIS lab. So we'll actually configure a point-to-point link between these 2 nodes on both sides. So we'll configure Ethernet 1.1 interface on SRL 1, and accordingly on SRL 2, we will configure the system 0 or loopbacks on both of the devices, and we will configure an ISIS instance. So we will have an ISIS area with a net ID, and we will add interfaces to an ISIS instance. We will create network instance of type default, and we will add ISIS protocol to it. So there is definitely way more configuration tasks in this exercise. And you will see how the code is, of course, more feature-rich and more verbose, and there are more stuff going on. But that is expected. That is because we have to deal with way more objects in this particular example. To begin with, I want to reset my lab to a known state. So I will execute the revert script that just reverts to checkpoint that we create for every lab with contain lab. So it will just go to the blank state as we just deployed the lab, and it will discard all the configuration that has been done before with previous exercises. So we are going to check out the V4 exercise, which has more stuff in it. Now, let's go to the main function right away. In this main py file, I have the main function that first initializes the Nornir. There's nothing crazy in this function, just a generic init Nornir function that comes out of the framework itself. And then what we do is that we run the configure node task. Of course, this is not a Nornir tutorial. You have to understand what's going on with Nornir to understand what's going on in this exercise. So we will execute the configure node task. So let's see what's going on in configure node. Now, in configure node task, we are creating an empty list of set commands, because what we want to do is we want to leverage the JSON RPC ability to combine different operations in this single RPC, and then we will set it out in one go to all the nodes that our Nornir will target, which means that all the replays and update operations can be bundled together as a single transaction, and they will be sent to all the devices. If any of them will fail, the whole transaction will fail and we will not have partially deployed stuff. So what we do here is that we create this point-to-point interface. But of course, before we kind of start to dive into this code, let's have a look at the YAML file that defines our hosts. So our hosts is an inventory that Nornir can work with. This one is a simple YAML inventory, as they call it. So in this inventory, we set the variables that our hosts have. So we have the SRL1 host, we have SRL2 host, and as you can see, they have the host name, the password, the data blocks that actually encode or contain the variables that we will use throughout our script. So we'll see that we have the point-to-point interface with interface name and IP. We have a loopback interface, again with name and IP, and we have an ISIS net number that we will configure for ISIS. So going back to configure node task that kind of launches all of that stuff, you see that here we have a point-to-point interface that is being created, and do remember that Nornir will execute this task for every node in the inventory, meaning that this one is going to run for SRL1 and the same task will run for SRL2. And the parameterization happens with the access to the inventory's variables. So here I say when I want to create my point-to-point interface, I'm getting the P2P interface container from the host, from the task and host, and I get the name. As you remember, point-to-point interface container has a name and IP, so we fetch this information from the inventory and we provide it to the default L3 interface function. I think it makes sense to have a look what this function does, but you will find a lot of similarities. This function basically just a convenience function that creates an interface, an object of interface class. It creates a subinterface, it creates an IPv4 container, and then we use these convenience functions that we discussed in example number 3, where we can attach an object to another object or create a relationship between them by using these convenience functions that we create for our convenience methods that we create for our classes. So here I'm creating an interface object, then I create a subinterface, then I create an IPv4 container, and then I will set the IPv4 container to my subinterface. And lastly, I add subinterface to my interface, and I return the interface back. So now my interface will contain a subinterface, and my subinterface will be configured with an IPv4 container that contains the IPv4 information that we got from the inventory. So a lot of steps, but this is exactly what you will have in your mental map when you approach to create to accomplish the same task. Okay, so this is how we created the interface. Then we add this interface command as a set command to a list of commands that we will eventually send to the devices. So I'm using the append function on my list of set commands, and I create a set command with an action replace. I use the path that is a property on the interface object, and I provide this object as a value. So now my list will be populated with different set commands, and each set command is an action. It's either updating a particular path with a particular value, or like here, it is replacing everything that sits under the path that is returned for this interface, and it will replace it with this value. Now I also create the loopback interface exactly the same. I reuse the default L3 interface function because loopback interface is just an L3 interface, at least in my particular example. And I add it again with a replace action to the path that is applicable to this interface. But then things get more interesting. So now we need to create a network instance, and we need to attach those two interfaces to the network instance. Now, what can I do with this? I need to fetch the subinterface from the interface. This is kind of getting more into the SR Linux lingua because some things are specific to the way that SR Linux operates. So we have a network instance, and interfaces need to be attached to the network instance. It's kind of like you need to have a VRF and then you add interfaces to it. Even though it's a default VRF, we still need to explicitly do that. There is a lot of explicit steps in SR Linux. We want to be explicit rather than assume things instead of a user. So we are getting the subinterface from the interface, and we need to attach this subinterface to a network instance. And that is what happens here. Default network instance, add subinterface, and that's how we attach it. Once we attached two interfaces, both point-to-point and the loopback, we create a set command with an action update. But now we use the default network instance path because now we need to add those interfaces to the network instance. It's not anymore under the /interface path. It is now under /network instance path. And we use the value of default network instance that we have created here. If you are still with me, there's just one more step before we are going to the demo. That is the ISIS stuff. And here in the ISIS instance, I'm creating an ISIS instance object using the class that I have created. Again, similar stuff, just like with an interface, we have subclassing from the Pydantic class. We provide some arguments to the class initialization, and that's how we create the network instance object. So once the ISIS instance is created, we also need to add interfaces to it. Same stuff probably for all the vendors. You need to configure your ISIS instance with interfaces. And I have a convenience function add interface. And then I use just variables, my circuit type, my ISIS level. And then I just add two interfaces, the point-to-point one and the loopback. And lastly, I need to add my ISIS instance to my default network instance protocols section, because that is how ISIS instance is attached to the VRF. So it needs to run in this default network instance. But that's it. Finally, that's it. It's a lot if you kind of looking at this first time, but now you have all of these reusable blocks. Whenever you want to create another ISIS instance, or whenever you want to create another interface and attach it to a different network instance, you have all of these blocks already ready, and they are all in the native Python objects and constructs. It's all fully typed in my case. You feel free not to use type hints, but I think it's super valuable to make use of types as much as you can. And then we just use the same SRL client, HTTP client that we used for the previous exercises. But now, because we have this list of set commands, we range over them and we add them to the list of commands that the client will send out. And then we send the set request, and then we just do a basic error check. So if the response contains an error and it is not a success, we just dump what happened, what the error was. And if there was no error, then we just return the good stuff, like we set the fail to false, and we dump the commands that we sent so that the user knows what we provisioned. Okay, so that was it. Let's see how it actually works. The goal is to have an ISIS instance running so that we can exchange system IP loopbacks between the two nodes, and we can start pinging from SRL1 to SRL2. I wanted to show you that there is nothing configured on the nodes. We cannot, for example, ping our SRL2 neighbor. When we execute this ping command, the error even says that there is a wrong value for network instance because it does not exist. There is no default network instance by default. We need to create it. That is something that our code carries out for us. But then you see that there is no way we can actually even ping our SRL2 instance. So what I will do now, I will install this watch that executes show network instance protocols ISIS adjacency command with 1 second refresh interval. So this is SRL1, this is SRL2. They both run the same show command. As you can see, the output is empty because we do not have ISIS configured. There is no even default network instance to begin with. And we will execute our example. Now we will use v4 main pi. This is our main entry for our lab. Now, what we expect to see is Nornir taking care of concurrent execution of our tasks. Our task creates an interface, default network instance, IP addresses over the subinterfaces, attach subinterfaces to the network instance, create ISIS protocol stanza, attach it to the default network instance, attach subinterfaces to the ISIS. So there's a lot of stuff happening in this particular function. So let's see how it works. Now, once I execute this, it will do the validations first, and then it will emit, create the payloads, and send it over to the both devices. Now, as you can see, we see the adjacency formed immediately. So it's all done now. It was really fast and quick, and it was definitely concurrent. We did not wait for a first request to happen and then a second one. When we executed this main py file, the Nornir provides to us the result object that we can print out with the print result function. So this is the result of the print result function. Here you see that we have these containers with configure node task being the parent task, and then there's SRL1 executing configure node, and that is what happens in the configure node task, or what we return out of it. This is our result object. So you see here that we have a list of 3 different actions or operations. So first we replaced everything under the Ethernet 1.1 container, and we added our configuration for the Ethernet 1.1. You see it all in this nicely formatted dict type. So you see the names and all the values that we provided or have been computed once we used the class initialization and provided the arguments to it. So we created interface 1.1, we created the loopbacks, system 0 interface, and then we created this network instance with type default. So now you have this full view, what you have sent to the SRL1. Because it's all green in these boxes, it means that it has successfully applied, it was not failed. And you see that everything that we have provided in these functions, the convenient methods that we used, have been kind of serialized and sent as JSON payload to the devices. Same you will see for the SRL2 and this same task. So this is quite cool and visually appealing to watch over the task or change stat that you sent to the device. Now, of course, we want to ensure that we can now also ping our neighbor from SRL1 because the adjacency is up, and hey, it's all working just nicely. So to summarize this, there are different ways how you can take your Pydantic models or Pydantify models and create a sophisticated or feature-rich network automation. You can start small with just function decomposition, make some reusable functions that you can then apply at different levels of your configuration object tree, or you can go all the way up to custom classes, inheritance, convenience methods that could help you build this relationship between the models, introduce testing and validation, do unit testing for your objects, and maybe then end-to-end integration tests for the full configuration provisioning. So the world is yours. You decide what you want to do with it. There are there's definitely different approaches that one can take, but there is no wrong way about it. Start small if you are comfortable with, and build gradually on top of your previous work. I hope you like this, and as I said, this Pydantify project is mainly run by currently 2 individuals, Urs and Dan. Thank you very much for bringing this project forward. it definitely helps a lot with network automation in a more programmable way rather than dealing with Jinja and all these pitfalls that you can find along the way of creating the templates and maintaining them and testing them. Thank you very much. See you next time.